Hello and welcome to ENGR 320 Thermodynamics Recitation on Chapter 1. So let's quickly recap what we learned in Chapter 1. So we have seen the significance and the far reach of thermodynamics in lots of areas, and we have looked at several applications, and dimensions and units are very important. This is a key aspect of engineering. And we also talked about open and closed systems and the intensive and extensive properties of a system. And we discussed the state and equilibrium. The most important thing to remember, which will help us in future chapters, is the state postulate, which says that the state of a simple compressible system is completely specified by two independent intensive properties. We also talked about processes and cycles, and we looked at what exactly is a temperature, how it is measured, what are the different scales, and we talked about pressure and variation of pressure with depth. Now let's go ahead and solve some problems. Pool of volume V, which is in cubic meters, is to be filled with water using a hose of diameter d, which is also in meters. If the average discharge velocity is v in meters per second and the filling time is t, which is in seconds, obtain a relation for the volume of the pool based on unit considerations of quantities involved. Okay, so we know that U has a unit, and maybe I should write this as a V. So V has the units of meter cube, and we want to write this as a function of T, which is in seconds, D, which is in meters, and the velocity. Let me write with that notation so that you don't confuse this V with the velocity V. So we want to write the volume as a function of your velocity, time, and diameter. So there are several ways to do this. All we want to do is try to use these variables and write a relation for the volume such that when we multiply d square with the velocity and the time, we get the units of the volume, which is cubic meter. And we wrote this proportionality constant here, so we're going to replace this with a constant by putting an equal to sign, and then for a round hose, you know that area of the cross section is pi d square over 4. So if you compare c d square with pi over 4 d square over 4, this implies c equals pi over 4. So the volume then is pi d square over 4 times the velocity times the time. Okay, all you're doing here is looking at the units and see that they match up. In this case, the extra step is finding this constant, which you can relate from the area of the cross section of the pipe. Okay, now let's move on to another problem. So the temperature of ambient air in a certain location is measured to be negative 40 C, and you're asked to express this temperature in Fahrenheit, Kelvin, and Rankine units. Okay, so we are given T, which is in degrees centigrade, which is negative 40. So you're asked to find all the others in those corresponding scales. So all you have to do here is to look at the conversion or the formula. So T in Fahrenheit will be 1.8 times T in degrees centigrade plus 32.2. T in Kelvin is T in degrees centigrade plus 273.15, and then T in Rankine would be T in Fahrenheit plus 459.67. Okay, so if you do the math, you'll get this to be approximately negative 40F. This would be 233.15 Kelvin, and this would be 419.67 Rankine. Okay, and this is the temperature where both the temperature in Celsius and the temperature in Fahrenheit will be about the same, which is negative 40. Okay, now let's look at another problem. The piston diameters shown in this figure are D1, which is this guy here, is 10 centimeters, and D2, which is shown here, is 4 centimeters. When the pressure in chamber 2 is, that is this pressure here, is 2000 kilopascals, and the pressure in chamber 3, which is this guy here, is 700 kilopascals, you're asked to find what is the pressure in chamber 1 in kilopascals. Okay, so in these type of problems, or in any problem, just make sure all the units are consistent. So you have centimeters here, convert them to meters, and you have kilopascals. So kilo is 10 to the 3, Pascal is Newton per meter square. So make sure you have consistent units. Okay, so to solve this problem, so we are after what is P1. Okay, let's do a free body diagram and represent all the forces acting. So you have force F1 here, F3 here, and F2 here. Okay, so at this point I can write F1 should be equal to F2 plus F3. Okay, and you know that you can write force in terms of pressure by multiplying with the corresponding area. So P1 A1 will be equal to P2 A2 plus P3 A3. So you can do a little bit of algebra here, and I'll let you practice that. So P1 will be P2 times D2 over D1 square plus P3 times 1 minus D2 over D1 squared. And if you put in the numbers and convert the diameters into meters from centimeters to meters, you get P1 to be 908 kilopascals. Okay, alright. So here the fact is pressure is force per unit area, so that's what we used, and we used the force balance to determine the unknown in the problem. Okay, so if you see that we have one equation, we have to have one unknown, which happened in this case, which we are after, and we could find that. Now let's move on to another problem. So you're asked to calculate the absolute pressure P1 of the manometer shown in this figure in kilopascals, and the local atmospheric pressure is 758 mm of mercury. Okay, So the way you do these problems is you start with a location, for example here, and then you keep moving around the tube, and then make sure you know the fact that two locations which are on the same horizontal plane will have the same pressure, so you can use that fact. However, if you see, you're given two different fluids here, fluid A and fluid B, and you're given kilonewton per meter cube as the quantity. So this is nothing but the specific weight is what you're given in the problem. So what I'm going to do is start with P1, right? And so this is P1 here, and then I go around the tube and it will be the same pressure here, right? However, I'm going up. The convention is whenever you have calculating the pressure depth variation, if you're going up along the tube, you should have a negative sign. So it will be minus rho A, density of the fluid, times G times HA, okay, which is this height here, which is 5 centimeters. And similarly, the same pressure will be seen here, from here to here, however it will be same here. So if you go up again on this tube, so again by our convention, it will be minus rho B G HB, and finally it has to equal to the atmospheric pressure, so equal to P atmospheric pressure, okay. And in this case P1 will be the absolute pressure which we calculate. However, we have to slightly simplify this. So P1 equals gamma, which is a specific weight, which is rho times G HA, plus gamma B HB plus P atmospheric. And make sure now you convert everything into consistent units. Your answer should be in kilopascals. So I'm gonna write 10 times 0.05, which would be in kilopascals, plus 8 times 0.15, which is the other height. I'm converting them into meters, plus we have to convert 758 mm of mercury into kilopascals as well. So from the back of the book you can find this. So you multiply with 0.133, divide by, so this is your conversion, and this is kilopascals. So your final answer here would be 102.7 kilopascals. Okay, so this is how you do these manometer problems. These are multi-fluid, and sometimes you would be given the density of the fluid, sometimes you might be given specific weight. All you have to do is realize what you're given and then make the appropriate modifications in your problem. Okay, let's look at another interesting problem. You're asked to determine the maximum amount of load in kilograms the balloon described in another problem can carry. And that problem is as follows. Balloons are often filled with helium gas because it weighs only about 1/7 of what air weighs under identical conditions. The buoyancy force, which can be expressed as listed there, will push the balloon upward. So if the balloon has a diameter of 12 meters and carries two people, 85 kilograms each, determine the acceleration of the balloon when it is first neglected. However, this is another problem. All we need is the first part of the information and the fact that they have given the density of air and they have asked to neglect the weight of the ropes and the cage, or also will be used for the current problem. Okay. So to solve this problem, what we have to determine is to see what is the maximum amount of load it can carry. Okay, so the forces acting would be the buoyancy force, which is taking the balloon upward, and the weight. And here, the many people would make a mistake. The weight here would be the weight of the contribution of the people and also the weight associated with certain mass of helium. So we have to compute that. Okay. However, we can compute the buoyancy force at this point since we know the formula. So F buoyancy is density of air, rho, and volume of the balloon, right? And then if it is a sphere, which is a good approximation, volume of the balloon will be 4 pi over 3 r cube. So you know everything here. You can compute the volume of the balloon. You know the density, you know the acceleration due to gravity here. So just be consistent with the units. You'll get the buoyancy force to be 10,296 newtons, okay, which is Fb. Now we have to determine the weight in the problem. However, they want the maximum amount of load, right? So we have an unknown there. So let's see how to do this. However, the mass total will be the mass of the people plus mass of helium, right? And since we know the volume of the balloon, we know the density of helium, we can go ahead and compute mass of helium as density of helium times the volume of the balloon, okay? And you know that the volume or the density of helium is 1/7 of that of air times the volume of the balloon, right? So if you do the math here, you'll get 149.9 kilograms, okay? And then for maximum amount of load, so at that point your balloon won't be going up, it's not accelerating. However, in general, Newton's second law says sum of the forces should be equal to mass times acceleration. In this case, the sum of forces from your free body diagram will give you Fb minus W will be equal to 0. Okay, so where this weight here will be m total will be Fb over g. So we know Fb, we know acceleration due to gravity. So this will be about 1050 kilograms. Okay, so that's the total mass. However, they're interested in the load, and in general, the load means people. So, and we said m total is equal to m people plus m helium. So m people will be equal to m total minus mass of helium, so which would be 900 kilograms. Okay, so that's what you're asked to solve in this problem. So all you have to remember is, which is a lot of you would falter here if you're not being careful, is to consider the weight of the helium as well when you compute the total weight. Okay. Alright, so this concludes the session for recitation or problem solving for chapter 1. Good luck with the homework. See you again.